Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so join me in welcoming Jorge Martínez from Denmark. He's here as a visitor. He was visiting a conference in San Diego and decided to stop by Microsoft Research, so I'm very happy to host him here in the lab. And the talk that he's going to give here is very exciting. The key thing is that it is about radio frequency processing. It is the stuff that is done in Motorola. He's doing his PhD in Denmark, in Aalborg University, but doing his productive also work in Motorola. So that's how Motorola gets the knowledge from the Danish university. So Jorge, please.
Thank you. Is it working? Yeah. Okay. Thanks, Darko, for the introduction. So let's start this up. Okay. So I don't need to say again who I am. Basically, what I will talk about is radio frequency architectures, and I will explain how this industrial PhD project works in Denmark. And I guess I don't know if something similar at all exists in the U.S., but it's a very good idea. So this is the outline of the presentation. I'll talk about this industrial PhD thing and what happened particular to me, where I started, and a lot of stuff has happened in only 2 years. Then I will talk about both my employees, the university in Aalborg in the north of Denmark, and about Motorola. I'll try to give you some facts about Motorola. Then I'll go a bit more detailed, and I'll talk about the PhD itself. What are the objectives of the project? What are we supposed to investigate? And then even more focused, some results that I have presented in a conference. At any time, if you want to interrupt me, it's okay to make questions, because I think we have a lot of time. So there will be time in the end, but if in the middle you have a question, just feel free. And also, if I start speaking too fast, please say slow down, or because I have the tendency to accelerate and non-stop. Okay. So this industrial PhD, it's basically a PhD degree, normal degree that I get from the university. And the objective is to approximate the companies and the university in Denmark. It's something that it's relatively new, like 10-year-old, and it's basically the Danish Ministry of Science and Education. They finance a part, so they give a kind of a scholarship, and I am employed by the company, and both the company at the university, they apply for this industrial PhD in the Danish ministry. And what they want basically is that the universities don't stay closed on their own world doing research in whatever, and then all of these results are not used to. I guess you have a very good system here in Microsoft, because you have your own research center, and this is the way it should be done, but not many companies have that, actually, I think. And I'll tell you, but Motorola, actually, they also have their Motorola labs and so on, but not in Denmark. So yes. So as I said, my project is proposed by Aalborg University and Motorola now, but I'll tell you what it was before. So Aalborg University, I guess actually it's a pretty big university or faculty for Europe. I guess for the US standards, it's probably a small one. I'm not really sure, but I could guess that. The Faculty of Engineering, Science and Medicine, it's the bigger one there, and actually there's a lot taught in English, which is a very good thing. And you don't, maybe in the northern part you find this, but in the southern, where I took my undergraduate studies, it's everything. There was nothing in English, basically. So it's pretty much an international university. Where I am, it's the RF group at the new center that was created in 2004, which is basically sponsored by a European Union project. Okay. So, about Motorola. Well, I say big blurry picture because I know a little, but I don't know much. And I just started Motorola maybe 4 months ago, and actually, when I started, that was when I met Darko in a conference in Greece, and it was kind of the introductory week where they give all these facts. But doing some short research, I know that it has over 60,000 employees. It's a pretty large company. I don't know, maybe same size as Microsoft, around that. And the headquarters of the mobile devices. I mean, the main. They also have a little bit. They work in very areas that I was surprised to know. But the main business is the mobile phones, the mobile device, and then they have also big in the radio, two-way radio, and so on. And the headquarters is in Chicago. It's a company that in the past few years it has been expanding. It's profitable, and expanding. I give you examples. So they bought our site, which we're 300, so it's not that big. They just bought another company. I don't know if you know TTP.com, and actually we're in the news very often that they're buying small companies, making a lot of acquisitions. It's currently in market share #2 worldwide, and it is already #1 in the US, and you can really see that everyone is basically carrying a Razer phone in here. They all have Motorola stuff.
#1, Nokia, or?
#1 is Nokia, yeah. #1 is Nokia. #2, I think, #3 might be Sony Ericsson or Samsung or something like that. Yeah, Nokia has been #1 forever, since it started, basically. So Motorola phones they're basically known by their very nice design, and usually we use in software-wise we use our own the phones, the Razer and so on. They have their own platform, but this is changing, and yeah, Windows Mobile it's really pushing hard in this business, and Motorola, I think the Motorola Q is the second phone that has Windows Mobile. Yeah. So what happened in my industrial PhD? Basically, I started a couple of years ago, and I started in Siemens Mobile, and it was the same site where I am now, and the project was proposed jointly with Siemens Mobile and Aalborg University. What happened after a year, BenQ bought Siemens Mobile, so not everything changed because it was kind of a weird buy, and actually the board of directors, it still got a lot of the same ones, and there were some Taiwanese from BenQ that entered and so on, and Siemens Mobile was losing basically a lot of money. And BenQ wanted, they were making mobile phones already, but they wanted a big name to get associated to them, and they want to really enter in this business. That's the way they found it. And basically, of course, you know, until the stuff starts ramping up, they continue losing money, and they had to somehow find a way to cut the costs. And one of the way they found was to basically close this site in Denmark because it's pretty expensive. And the solution that our directors found was very good because they basically we were sold to Motorola, which is a very good company. It's doing very well in this very volatile business, and they're really growing a lot in these past years, Motorola. So this was very good, and I have basically in my short career I've already worked in 3 big companies, and I've never changed my office. So it's quite an achievement, I'd say.
Pretty good.
Maybe it doesn't look that good with so much rotation, but Yeah, that's what happened.
I have changed 3 offices in one company. I think yours is better. This is definitely the case.
Okay. Yes. So basically, people in the site, 300 persons around that. Actually, with this bot of TTP.com, there are people joining in, and the site is, it's always going up and down. And in the crash, it went down to maybe around 200 people in 2001 or something. And now it's been growing, and it got a bit steady with this BenQ stuff, around 250. But now I'm not sure the numbers, but I think we're already 350, so it's growing. And basically, what Motorola wants us to do is a complete phone, complete mobile phone, from beginning, from definition to the end. They say we want the phone like this and like that. That I cannot reveal, and basically they just start and do everything of it. Not production line, because we don't have, but development. And the production line is in Germany somewhere. So, talking a little bit more specific about the project. Basically, the project is situated here in the RF front end of a mobile device. So battery operated and small. This is the 2 big things. And basically, what the RF front end has to do is, after we generate the signal, or receive it, depending if you're looking at transmitter or receiver, we have to convert it to analog. We have to up-convert it to the right frequency, so we can send it to the antenna. Of course, this starts to get more. If we have just GSM, it's pretty simple nowadays to be done in a small and efficient way. But if we have a conjunction of different standards at different frequencies, it starts getting more and more difficult, both in the signal generation, because with all the coding and all that modulation stuff, you need to do a lot of processing there, but also in the RF front end, because different frequencies we need to up-convert and we need to send at the same time. So, yeah. And as I said, nowadays we have the 3G, the UMTS, which is basically one standard. And this is supposed to do voice, supposed to do data. So we're supposed to be able to navigate in the internet fast. Well, it's not that fast, because actually it's around 384 kilobit per second, which is not that good. So people, and it's supposed to be in operation for, I don't know, 3 years or 4 years, and supposed to be profitable. And I don't know how it is in the US actually, but in Europe it was a huge transaction just to buy small spectrum, like 5 megahertz in spectrum at the right frequency. It costed billions of euros. And it was basically, it has been a failure basically, and it's still, even today, it's not really. People are buying now 3G phones, but it's not didn't pay off yet. So already a few years ago, people started thinking about 4G, something faster, and Aalborg University has actually been doing quite a lot of research in this 4G thing. But the question is, what is 4G? Okay, it's something faster, but how do you define it? Is it one standard, or what is this? And try to explain you this. I will show you how it's looking today in the cellular and world. And basically, I have the mobility here on the epsilon axis, and the data rate, so the speed, transfer speed in the x-axis. And what we see is that nowadays, and actually now we're more here, we have one standard for everything. And as the data rate starts growing, we cannot have such a standard that it will be able to work with high data rate at very high speed and stopped. And how is it looking now already is that we're having specific standards, like wireless LAN, WiMAX, which is an improved version of wireless LAN, if you want to call it like that, that are increasing our data rate, but they don't have enough mobility, for example, to bring in your car. And what's happening is that it's basically building up with several standards to do the different to different mobility you need. And this is the way it's looking, and this is probably how you define 4G. A conjunction of standards, not only one standard. So 4G is not defined at all. It's something, this is my vision, this is the vision we have at university, and it's probably the way it's going to be. There won't be another UMTS2 or something, whatever. There's the evolution of UMTS is the HSTPA, it's here, which eventually can achieve 10 megabit per second. Okay. So 4G. Basically a conjunction of standards, like I said. And if you look, maybe in 2010 we'll have a phone, which will not build this one, but that it could have one-way communications like digital video broadcast, digital audio broadcast, satellite communication, GPS, or the European Galileo, which is the same principle. And then we'll have a conjunction of standards for indoor and some wireless LAN, some wireless PAN, like evolution of Bluetooth or something like that, and some more with mobility. And this, you have to add the WiMAX, and then you have to add maybe HSTPA or something like that, GSM, maybe even just for voice. So we'll have really, really a lot of standards, and all at different frequencies, all with different bandwidths and so on. The thing is, if you look in yellow, all of them have the ones in yellow, they are operating with OFDM. I don't know if you know, if you have heard about, probably heard about. I don't know if you know what it is. And the thing is, OFDM is going to play a big role in 4G. That's for sure. And I will explain you what OFDM is. Okay. Don't want this to be like this. Okay. Basically, if you look at how it is, like imagine this as in frequency. It's a frequency signal, and imagine this. So frequency is here the x axis. So imagine this is like a radio station transmitting at a certain frequency, 98 point something. What happens is that we cannot really filter that sharp here. So basically, we need to have a guard band until the next radio station comes. And the problem is this is very inefficient because we're using this guard band, we're wasting it, basically. And you know, as you see in UMTS, it was frequencies really, really expensive. And it's something that, of course, you can always go very high in frequency, but you'll have a lot of problems. You cannot really make the thing work. So we have to use the spectrum we have available in very, very efficient way. And the FDM, that's what it does. It basically the same pulse here, and it's exactly the same concept, but it's orthogonal, which means that when one is maximum, the other is 0. And then you can do this with as many carriers as you want. They're just as close together in frequency as possible, basically. And of course, this was invented some years ago, but they could not do this because then you had to filter very, very much. And so you cannot, it was impossible. And if you had 5 carriers, you have to use 5 very sharp filters, and this was basically not feasible. But what it took really a great step was with the invention or whatever of, and also the processors. They can do this fast Fourier transform. And by this, you can just take, you can receive the whole signal, and then by fast Fourier transform, you can take the carriers you want at the frequency you want. And this is the difference between the FM radio you have and the DAB, digital audio broadcast, which is getting quite popular in Europe. So, see, I forgot something. Okay. Of course, it's how to say this? Yeah. Basically, if you look, this is in the frequency domain. If you look this in the time domain, it's the same as getting a high data rate stream and dividing it in low data rate streams. and sending them in parallel. Yeah. Okay, I won't go into this detail. So, what are the advantages? Spectral efficiency. This is the really great advantage, and this is what we want, because we want to increase the data rate, but we don't want to use a lot of bandwidth. It's very simple to implement nowadays with the FFT, and I won't go in detail here, but it's very tolerant to inter-symbol interference. Disadvantages: we have to use some kind of guard time anyway between these chunks of carriers, and major problems with for us in the RF part, it's those two. And one is that, so a frequency and phase offset of the carriers, the tiniest, the orthogonality is lost, and all the concept is gone, basically. So one is not zero, so we're basically having interference between carriers. And another thing is the peak to average power ratio. This is the great problem to the power amplifier, actually, because what happens is that if you imagine all these carriers in the frequency like I showed before, if in time, if they're all transmitting like they were before, if they were sending a pulse at all the frequencies, and if you have 1,000 of them, and then if you're doing this at the same time, so different frequencies up there, always transmitting at the same time, the thing all this thing will add up, basically. So it will get 1,000 times larger than if you're transmitting only one. And of course, this probability-wise, it doesn't happen that often, but it can happen. And when these huge peaks come, and in wireless LAN it's something like 6 to 7 dB, and this is a reduced value. If you calculate it, I think it's something like 11 dB. So you can have a peak that is 11 dB larger than your average signal. And this is a really great problem to the power amplifier, but I will come back to this a bit later. So standards using OFDM, so that I told the DVB, the DVB, the digital video broadcast. And this one, it has an option that uses 6,817 subcarriers. And if you calculate, the peak to average power rate can be around 38 dB, which is huge. But actually, in practice, it goes to, I think, 12 or something, because there's a lot of schemes and used in the digital part to reduce this, and the coding and so on. All of it, it's basically to reduce this. But if it was used just like this raw, it would be impossible to be used at all. Then wireless LAN, which I think peak to average power rate is around 6 as it is. And then this WiMAX, it's also using OFDM, and this is something I don't know about in the US, but in Europe it's ramping up, and it's coming quite fast. Okay.
What's the power consumption on the WiMAX?
The power consumption?
Is it really, do you actually spend a lot of energy to communicate, or?
You do. Especially because of this peak to average power ratio, and especially because I'll come back to that later, because it's very different to GSM, for example. GSM, it's quite easy to make. The bigger thing actually here is the power amplifier. That's the one using the most power actually, and the problem is that these have information in the amplitude, and I'll come back to this. So this is the really big problem to a mobile device, battery operated. Okay, I'll explain you what MIMO is, but this was what I was supposed to go into in the project, but I'm not. But just for the sake of I don't know if you know what it is, but just if you ever hear it again, then you at least have an idea what it is that we're talking in here. So basically, what we do now is have a cell phone and a base station, each one with one antenna, and there's a channel between them. And we use this channel, good or bad, and that's it. That's what we get. What MIMO does is that someone said, why don't we have more than one antenna in both ends? Then we can explore all the different channels and all the different combinations. We can explore diversity, which is basically one antenna receiving the two streams and then seeing which is the best channel and deciding it, or just maybe combining both. Then there's a lot of algorithms on top of this, and of course there's a lot of channel. It very dependent on the channel and how these channels are correlated. In a mobile phone, I mean, it's so close to that maybe the correlation is so high, they're so alike that maybe it doesn't even make sense. But in a laptop, it could be. I mean, even in a mobile, in some time, because of course it will depend on the frequency and on the wavelength, how close they are. It's relative to that. So it's something that has been very, very hot in the research in the mobile in the past, I don't know, 5 years, maybe more, 10, I don't know. But mainly in this in the channel and channel modeling and so on, and the top level algorithms for networking. Question is, in the RF, what do we do? I mean, should we just replicate our? We have to have RF front end here. Should we just replicate it and have two of them? It's really not, I don't know, that feasible also in the mobile for now. But I won't go more in this detail because that's actually something I didn't look at it. So the project is, I'm focusing only on the transmitter side, so power amplifier, no receiver. And the huge problem is this efficiency linearity of the power amplifier. And I'm considering a OFDM wireless LAN signal. I propose a new architecture to actually, in theory, it solves this problem. If you just look in the simulation, and if you look at it, it's perfect. But implementation-wise, there's a lot of issues, really a lot. And the concept of it was invented, I don't know, 60 years ago, and it's not because of all these implementation issues. There's not a single product that uses it yet. Yeah, so I have to change presentation. Now maybe to go a little bit more specific, but I will spend more time here in the introduction. Okay, basically, the architecture is a polar architecture, and I'll tell you what's the difference to what's used nowadays. And then basically what I'm solving here, it's a problem that this architecture it's a major problem. And go more in detail. Okay. So I'll just try to explain you. First of all, try to give you the area, even though I just already talked quite a lot about it. But I'll try to explain you the architecture proposed, some of the modules, the architecture, and one of the problems that we solve with this group delay equalization. Okay, so introduction. Basically, these modulation schemes, so OFDM and not only, so UMTS also. We are changing for something that it looked like this. For example, GSM doesn't look like this, but it's similar. Something that only has information in the phase. So basically, if we consider that we can only move from one point to the adjacent one, we are just changing the phase. The amplitude is still it's the same. What happens is that now we're using much more complex modulation schemes, like QAM, 64 QAM, whatever. And in here we need to carry information in the amplitude of the signal, or in the envelope. I will say amplitude and envelope, it's the same. Of course, the objective is just to increase to have higher data rates, and this can increase and increase. Of course, then the spacing between them will be smaller and smaller and much more complicated you have to be much more precise to decode this. And there are great problems on the amplifier to achieve the same efficiency and linearity, and explain why. But to make it even worse is the OFDM signals and this peak to average power ratio I talked. So we have these huge peaks coming also. Besides being not constant, the envelope, it's even with huge peaks. And the problem is that if you look in the power amplifier characteristics, it looks typically like this. This is basically the input power and the output power. So when we push the power amplifier to a certain level, it starts compressing. And this is something totally nonlinear. So you don't know what, when you send here, you know exactly what you have in the output. When you send up here, you don't know. So, and at a certain point, of course, it cannot send anymore, power amplifier. The problem here is that in these very low points, when it's linear, so we're getting in the output what we want, it's very, very low in efficiency. So basically, it's using a lot of power that it's being wasted. It's just dissipated. So what happens is that when we have these big peaks, we have to expect for them, and we don't want the peaks to go in this compression part, in this nonlinear part. So we have to operate the power amplifier very much low. And when these peaks come, they're still linear. So we're not distorting the signal. This means that the efficiency goes down dramatically. And this is something that, in GSM we can operate it perfectly here. We are distorting the amplitude of the signal, but we don't care because there's nothing there. There's no information there. In this case, we care because there's information there. So we have to operate in very low efficiencies, and this is something like it goes down to, instead of maybe 60 or 70% in GSM, it goes to 6 or 7%. So it's directly related to the talk time when you're talking on the phone. So it's 10 times less, and this is, I guess, why UMTS phones have, when you operate them in UMTS mode, it's really low talk time. And wireless LAN, it's even worse because of this peak to average power ratio. It even adds up, it's even higher peak to average power ratio. So this is how it's done today. You send the signal in the PA, and you have to send it very low, in very low input power. So you expect the peaks not to go in the distortion area. Okay. So if you use a GSM architecture on your wireless LAN and just change the input signal, and of course you have changed the frequencies and so on, you'll get efficiencies of 2 or 3% or something like that. So basically, a battery doesn't last more than a few minutes talking. So something has to be done, and what I propose is a kind of a polar architecture. In opposite of sending, so what it's done today is that you get the Cartesian coordinates, basically the I and Q. So as you saw in the constellation diagram, as I showed before, basically, again, these points here. And what it's done today is that you just send this signal up here to the power amplifier. And if the signal is doesn't have information in the phase, it's really okay because the power amplifier is distorting the amplitude and you don't care. But in this case, it's a problem. So what I propose to use a polar architecture where you separate the amplitude or envelope and the phase of the signal. Meaning that in the phase path here, down here, we up converted, and we drive the PA with a constant envelope signal. This means that you can use a switch mode power amplifier, which is basically on-off. So it's amplitude-wise, it just kills everything. It distorts completely, but we don't care because we only have the information is only on the phase of the signal. It's not on the amplitude. And here the trick is that you have, and this restoration, it has been invented, like this is what I'm saying, 50 or 60 years ago. And the trick is that we restore the signal here in the power supply of the power amplifier. Restore the envelope there. And this is doable. And we can achieve, very high efficiencies because this power amplifier here, it's operating in their high efficiency mode, say. Then the problem will be that we need to get the envelope signal, and we need to amplify that one, right, before we go in the power amplifier. And then we also need to care about this guy here, this amplifier here, which again, it can be used the same concept that we can drive it with a constant envelope signal. And how do we do this? We do this with this pulse width modulation. Basically, we have the envelope signal, and the information in the envelope, it goes on the width of these pulses here. And this is easily done, actually. And furthermore, I will talk a little bit about this Delta-Sigma modulation, which is kind of a noise shaping technique, and I won't go that much in detail there. But this is basically to make this one also efficient, because this is the one connected to the supply. So it's very, very important that this is also efficiency. It's really efficient, because this is also playing a big role. And the thing is that we have such an on-off signal, and we want this signal just amplified. So we need to filter it out. And just by simple filtering, we can recover the signal here. Now, yeah. Okay, so something like this, polar architectures have been for a while here, and they're using it in Edge, I think, not in UMTS as far as I know. In Edge it started to appear, not exactly like this, and it's not really much better than the traditional Cartesian architecture. So something like this, if perfect, would be like actually, in theory, you can have efficiencies of 100%, which you cannot have with a linear amplifier, because these guys here can just be 100% efficient in theory. In reality, this goes down to 60 or something like that, which is already very good. But one of the problems that you might look here is that what if the signals are arriving at different times in the power amplifier? This would I'm basically recombining the wrong things. So this would kill the whole thing. And the problem that we're looking here besides this is that we have actually components, and mainly the filter where the delay introduced, it's actually depending on the frequency. So if this delay here depends on the frequency, how do we compensate here on the phase? I mean, it depends on the frequency of the envelope signal. The phase, we don't have the envelope. So how will we compensate this? With what value? And how it's usually done, it's just a constant value, and there's of course some degradation. And the degradation is in error vector magnitude, which is basically so how you measure it's what you get here at the output, the constellation diagram, and what you should have got, and it's the difference between that. And the spectral regrowth, so we look at the signal in frequency, we look at the spectrum, and basically we have, I'll show you afterwards actually. So this is the time signal, and this is the envelope signal, this is the phase, and I just shifted for 4 nanoseconds, which is basically nothing. And this is the output, the envelope of the output signal. So if you look in the frequency, so what I'm calculating here is the spectrum, the power spectral density actually of the signal, and we have our carrier here. So it's actually not upconverted, but it could be. So this frequency could be wireless LAN, I don't know, 2.4 or 5.2 or whatever, and the bandwidth of the signal, and then we have to comply with this mask here, which is in black. And this is what the regulators say. You cannot, it cannot be up than that, more than that. And the thing is that just with 4 nanoseconds, we are already not complying. So it's really, really, really tough to do this, to make this work. In terms of this error vector magnitude, it's never a problem actually, and I won't just talk about it anymore. But it's usually that's easy to. It's not. It's easy for this problem here to work. Thing is that, as I said, the delay in the envelope, it's varying with the frequency of the input signal. So I tried and I looked at different Butterworth filters, very high order, and with different cutoff frequency. So basically, if you look at the amplitude characteristic would be, something like this, and then one that it's cutting off further away. And this is how the group delay looks. So the delay that it's introducing to the signal. And it varies. If you see the one where the cutoff is smaller, it varies something like, if you look in the bandwidth of 20 megahertz, the input signal is actually 20 megahertz, the IQ signal. But the signal you have, the envelope signal, if you just take from the IQ the envelope, it's a square root, and then it has both of them squared, under. So it's very nonlinear operation. So basically, this envelope signal, it's very, very. Basically, when you apply a nonlinear operation in such a signal in frequency, what happens is that it's completely spread out. And this is the envelope. It's very, very spread. So it's difficult really to define the bandwidth of this envelope signal. But if you look at the IQ, it's something like 16, but okay, let's say 20. The thing is that this varies like 40 nanoseconds. And I just said, okay, we cannot have something 4. So what do we compensate in the other path? Because we have in the other, we have to give some delay so they arrive at the same time. So what delay do we give? I mean, when we have this variation in that path. The thing is that you can make in digital filters, you can actually make with a kind of a sharp amplitude cutoff, maybe not as sharp as we want, and you can make something that introduces just a constant delay. There's no which we call linear phase filters. But it's not really feasible in analog, and especially with these requirements of being passive, or at least as passive as possible, not use that much power and size. So we have to deal with this thing here. And I tried, in the next slide, I tried using this filter, which has really a lot of variation, and the one which, if you look in this bandwidth, it could comply with the 4 nanoseconds. And in the phase pad, I'm just compensating with a constant delay. And what happens is that this is the one that has a lot of variation, the blue, which is not complying with the mask, and the red is the other one, which is complying with the mask. And I actually found out that it's not only because of this variation, but it's also because of the it's also because of the increase of the envelope signal bandwidth. Of course, if we're filtering further away, we have we get more of the signal, and it's very, as I said, this signal is very spread. So this is another reason. And if you see this, it's appearing something weird here, some kind of spike, and this is because of the Delta-Sigma Modulator. And maybe I won't go that much in detail here. Basically, Delta-Sigma modulation is something that, so first of all, it does this pulse width modulation. So we have the information of the signal it gets in the pulse, in the width of the pulses. But what it does is that we need to. It's also a digital to analog converter. So when you convert this, there's always some kind of quantization noise that it's added, because you're passing from levels to something that it's continuous. The thing is that this delta sigma is basically doing some noise shaping, and using this noise created from the conversion, it's basically putting the noise away from our signal, for our passband. And I won't go much more in detail, but what we can do is that we can change the sampling. So if we sample much higher, we can shape the noise further away, or we can increase the order. But of course, it doesn't come for free. And just show here, when we increase the order, this is the noise transfer function. This is in frequency. And if we see that our signal is basically here, when we are increasing the order, so from the blue to the green, basically the noise is being shaped further away. When we're increasing also the sampling frequency, basically our skirts here, this peak that you've seen before, is going down. The thing is that when we increase the order, there will come problems with the stability, because we have all these loops, if you've seen before more or less in the diagrams. And to have this stable in higher bandwidth, it's very tough. So it's not really that simple. and also increasing the sampling frequency, it will just increase the power consumption. We just have to, sample much more times. The power consumption from the modulator itself and from the amplifier, but I'll just tell you about this a little bit just fast. So basically, we could do this, but we could also do a sharp analog filtering to get this quantization noise out. Then we could use one with very low sampling frequency, very low order, if we could just filter here, right? The problem with the filter is that it's introducing the group delay. So we have to do something in between. Basically, these are the results, and that without anything, just of this. And we need some cutoff of around 18 megahertz just to comply with the mask. And ideally, we'd have something like 25 or something like that. And actually, when we increase the order, there's not much difference in both. So this is the EVM, and I won't talk about in the left, because this is the limit, and it always works, basically, even without what I'll show you later, so it's not really a problem. This is the critical point of the mask. So it's the 30 megahertz knee. It's usually when it starts not complying with the mask. And the thing is, this is where we have problems, right? And we cannot use very sharp filtering. And when we use higher, we have okay performance, which is not that good, because not much more. If you start including all the imperfections of the other components, this margin here of 6 dB is not that good. And this is actually done with very high sampling frequency, which is maybe real in maybe 4 or 5 years for such a modulator. But for now, maybe actually more, if you consider a mobile device, battery operated. So the thing is, if you want to use this filter, we have to compensate for this group delay. And this is what I propose to be done, and to compensate for this. And basically, it's to use a kind of a mirrored group delay. And we can do this with a digital filter in the digital signal processor quite easily, quite a simple filter. Basically, an all-pass filter. We're not changing the amplitude, we're just changing the phase. So we're kind of pre-distorting, if you want to call it like that, the phase of the signal. And if we get this group delay here, depending on frequency, we will totally compensate for this, and we get something which is constant. And then in the other path, we just send something constant, and then everything is perfect. Okay. So applying this to there. So I'll show you basically this is the improvement. So it's comparing this graph with the other one. And we get an improvement of like max 2.5 dB in the area which actually we're interested. We're not that interested in up here because of the quantization noise, to just make it impossible, Delta-Sigma Modulator. And down because we actually doesn't work because we're just filtering too much of the signal. The thing is that, okay, the improvement is good, but we actually expected more for this. And I made this and I tuned the parameters of this filter, this all-pass filter, manually. And before thinking, how can we make an algorithm that will tune this and make this even much better, I tried to find out really what's the fundamental limitation of this. And to do this, I just tried a filter that it's not feasible, but in simulation we can do it, and which is basically a free filter, so linear phase, doesn't introduce any group delay, and very, very sharp, and kind of a perfect filter if it could exist with those characteristics. The thing is that with such a filter with no group delay, we have the same, so the curves are basically on top of each other, as when we use this group delay equalization procedure. So meaning that even if we compensate it perfectly, we will not get any better than this. And another thing you can see is that, okay, this is the point I'm talking, 30 megahertz. And okay, there's a small improvement. Yeah, you cannot. It's actually from the light one to this one. So this is a case that actually there isn't much improvement. But the big improvement is really here, close to the signal passband. And I mean, here I mean, this could be something very good when we have a real power amplifier in there, and then we are all of a sudden not complying with the mask up here. And this could give you it could give you actually quite a lot. It could give you a 10 dB difference, and or maybe 5, 6 if you just go a bit further away in there, and it could really save you. And it's very simple to be implemented. Okay, so jumping to conclusions. So basically, what we find is that there are two reasons why there's a spectral regrowth. And one is this group delay variation that it's introduced by the filter. And this is what we approached here. The other is that we're reducing the envelope bandwidth, which is very, very spread. Basically, we're trying to solve this one. We succeeded in that, and we found out that the improvement is not that large in the critical point. But before that, it's actually very, very, very large, and it's very important close to the passband. Further away further away from the passband of the signal, what is important is the envelope bandwidth, and we have to let as much pass as possible. Problem is the Delta-Sigma Modulator, which is putting noise there. So it's really, you have to balance it, how to do it. And of course, you can, by increasing this, you can do a Delta-Sigma Modulator that's better, that it shapes the noise even further away. The thing is that, in principle, you'll have to use higher oversampling, and this would increase the power consumption of the modulator and of the amplifier, because higher oversampling means that there's much more transitions, much more. The switching is much higher. So basically, the amplifier, it's switching much more. And in the real world, this amplifier is perfect, but in the real world, no, in the perfect world, but in the real world, the amplifier cannot really follow these switches, these pulses, this kind of digital signal. So there's always switching losses there. So it would be less efficient. So the thing is, we have to be very careful on increasing the envelope bandwidth without destroying or without just increasing the power consumption exaggerately. Okay, so that's the end.
Thank you.
Thank you.
I have one question, but not exactly related to your results. You spoke when you did you considered only the phase information for constructing the filter, saying that information is really embedded in phase.
Yeah.
But what I have learned from my background in speech is when you have noise present, it doesn't really affect the phase.
Yeah.
What it affects is the amplitude. So when we do a noise speech enhancement, we work on amplitude rather than phase.
Yeah.
So the point where you disregarded the amplitude and only worked on phase, is that?
Let me see.
If you can go back there to the slide where you.
Here.
Yeah, here.
Yeah.
You mentioned that the real information is in the phase down.
Yes.
And you considered that thing.
Yes, the phase information is here, but the envelope is here.
Okay.
So it's like I calculate just the amplitude here, the A, and the phase information, which is here, and then you can just take the phase right by a tangent. It's mathematically simple. I just calculate this way just to up convert. So basically, we have information here and here. Right? So it's separated in that. That's why it's called a polar. So we separate it in amplitude and phase, right? So how it's done now, it's usually separated in I and Q, Cartesian, X and Y, right? So noise will be present in both.
Both?
Yes.
Okay.
Noise is. I mean, all these things are introducing noise, and you have a noise floor and.
Okay. That is a quantization noise or other noise which is
introduced
by those components?
No. Yeah. There's always the noise, what do you call the white noise. That's all over the place. But this quantization noise, it's here. It's in the envelope. It's in the envelope, yeah. It's not in the phase. But actually, you could have this delta sigma modulation and this digital, because we have to also have digital to analog converter here. So it can easily, I didn't look into it, but it also should be actually used here. So I suppose there will be also some noise on the quantization noise, but in the phase. But as you said that it didn't matter on the phase, right? Yeah, that's correct, because I think this phase signal, it's very, very, very narrow signal. So basically the quantization noise is just too far away, I think. It's very, very different. This signal is something that it's very spread and very large, and this phase is something that it's very, very narrow, very close to the DC, you know, to the. So maybe that's the reason where this noise wouldn't matter, I guess. Thanks.
Thank you, George, very much.
Thanks.
It was a pleasure to have you here.
It was great to be here.